Okay, in this lesson today, we're going to mostly practice things that we've learned previously, and also we're going to throw in a unit from, I think it kind of goes more with Unit 9 than it does with Unit 7, but it's from Unit 7. And these two deal with delta G, delta S, mostly the, not mostly, but delta G equals delta H minus T delta S. Any of those ideas, we can attach those to these questions, or many of these at least. Okay, so let's get started. So we've seen this kind of situation before, but we just didn't know anything about delta S at the time or delta G. This one doesn't have any answers that deal with delta G, but we, like always, we already know the answer. Answer's A. And let's look at this. So here we have water. Here we have salt. And here we have an ionic dipole interaction, aqueous salt. Okay, so let's talk about these columns here, breaking and forming. And let's look at the delta H's. When you break bonds, energy has to be absorbed. So delta H has to be positive. So we can get rid of C and D because of that. Breaking, again, have to be positives. So we didn't eliminate any more answers. And then delta H forming, you have to release energy. And that also didn't get rid of any extra answers. So now we're down to A and B. And let's see. What do we have different in those? Delta S is disorder, change in disorder, and we have basically NaCl solid going to NaCl aqueous. And that's going to be a overall an increase in disorder, but let's look at the individual parts, I guess. If we break something up, that should give you a delta S positive. It should make it things more disorderly. If you break something up, again, that should make it more disorderly. And if you form something, that should make it more orderly. So I guess that's why we got answer A. We didn't really get to look at the overall because none of these columns deal with the overall reaction. Second question here. High solubility of an ionic solid in water is favored by which of the following? Like always, we know the answer. So it's got to be because of that. Let's see if we can kind of figure this out here. Oops. Let's see if we can use this idea. I don't know if we will or not. Increase in entropy. So that would be a positive. Formation. Formation, when you form bonds, energy is released. So let's put a negative there. Would that help you get a negative value for delta G? And I think it would. So that's how we got the answer D. We have a couple questions here. Again, we got answers already. D and B. We have a bunch of thermodynamic data. Under which of the following temperature conditions is the reaction thermodynamically favored? So, well, at 298 it's not favored, so it can't be favored at all temperatures. But let's look at this further. Delta G equals delta H minus T delta S, and let's put our delta H and delta S signs in there. And I think if you look at those signs, you could never, no matter what temperature, get a delta G that's negative. Okay, since it's not thermodynamically favorable at 298, or in this case, any temperature, that means that you have very little of the left to right, but you have lots of the right to left. And that is indicative of a K that is small. So that's how we got to answer B. When I say small, something like, I don't know, I'll just make one up here because I don't know the answer to the K value, but maybe that kind of K value. Again, that was just a guess. This one's kind of a tricky question here. This is definitely a thinking question. There's probably a number of different avenues to kind of get to an answer here. You could kind of use a system of equations kind of style. By the way, do we have an answer? We do. B. Closest. So we're not actually going to get an answer that's going to be exactly dead on to 300. So we have all these bond enthalpies, but we want this bond enthalpy. Well, that bond enthalpy is not given. Could we use these ones to get that bond enthalpy? This is the style I chose, but there's probably a lot of different avenues here. So if the N to the H is 390 kilojoules per mole, and O to the H is 460, if we kind of think about like if A plus B is this and if B plus C is this, what's A plus C? And so we could kind of, there's a commonality there with H. So then the N to the O is, we don't know exactly, but I'm going to go 460 minus 390. It's about 70 kilojoules per mole. Let's go with another if. If the C to the O is 360 kilojoules per mole, and that N to the O is about 70 kilojoules per mole. Let's see if we can get another commonality here. We could figure out what the C to the N is. 360 minus 70 is about 290. And our closest answer to 290 is 300. So maybe you learned a little bit of that in maybe even back in geometry class. I'm not sure if that's where you learned that or not. Back in the Stone Age when I learned geometry, that's where I learned that idea. Okay, we have a couple questions here. Again, we got the answers already, D and B. So let's kind of break that down. What do we got here? Which of the following statements identifies the greatest single reason why the Kp has such a large magnitude? So Kp is large. That means delta G must be negative. So why would the delta G be negative? It might be, let's see if we can get anything from using this idea. I don't know if we can or not. So if we want delta G to be negative, what do we know here? We have, up here we have two gases going to two gases. So that's going to be a little tricky. So we're not quite sure on that, but we have this negative value here. What would happen if this was negative? That would certainly help into making this a negative. Do we have any answers that deal with that? Well, activation energy, we know that's not going to be a reason. Delta S being small and positive. If it's small and positive, that makes this small and negative. So that certainly can help make the delta G negative, but this small amount certainly, if this was positive, wouldn't be able to make delta G negative. But how about if the delta H was large and negative? That means that this is very overpowering as far as a number is concerned. So C and D are both possibilities, but D is a much better possibility than C. Number 43. Value of enthalpy change per mole for hydrochloric acid. So this is going to be a Hess's law question, but a big but here. In this overall reaction, when you put these Hess's law together, we're going to get two hydrochloric acids, but this one's per mole of hydrochloric acid. So when we get this answer for the Hess's law, we're going to have to divide that by 2. So let's see what we got here. Let's go blue for this one. We need H2 as a reactant. There it is. So that means we're going to use 4 kilojoules per mole, as is. Chlorine, and there's chlorine gas. So we're able to add 242 to that. Don't have to do anything. And we need 2 hydrochloric acids. We already got 1 there, and then we have another one there. So it looks like to me that we're not rearranging any of these. But remember that when you do this Hess's law, that's going to be for 2 hydrochloric acids, but we went for 1. So you're going to have to divide that number by 2. And that's how you got to negative 121, sorry. Question 6 of 7. Let's make sure we finish that one. Oh, wait a minute. I knew this does come out to be, if you add these up, I think that comes out to be negative 186, and then divide that by 2. I knew that something was a little wrong there. I just, I don't know why I circled B when it said it was A. But okay, let's go to our next question here. So it looks like this is a free response style. We have some moles. I don't know if we're going to need that. I don't know if we're going to need that. But I have a feeling we're going to need... Oh, and that says released. That's going to be important. And maybe we need the delta G too. We'll see. Calculate the delta H for this decomposition. Well, delta H is nothing more than the kilojoules per mole. So we have kilojoules and we have moles. Now it says released, so you have to know that that's a negative. Okay, so that's how many kilojoules per mole for that decomposition reaction. Which is larger, products or reactant bond enthalpies? So remember that over here, bond enthalpies are positive. Okay, you have to break those bonds. And then over here, these are all bonds formed. They have to be negative. Well, what's our answer? Our answer is already negative. So that means these negative values have to be greater. So products, and I think I just justified my answer there. How does the presence of a catalyst affect? It has no effect on the enthalpy, the entropy, the free Gibbs energy, nothing thermodynamically. It just makes the kinetics go faster. It makes it get to its, in this case, endpoint faster. And there's all of our answers there, and we've already talked about those. I think this is our last question here. Okay, so we have, looks like this is cellular respiration, but this is in a calorimeter, so I don't know if we can really call this cellular respiration anymore. Calculate delta H. So we have grams and we have kilojoules. So last time we had moles and kilojoules. This time we have grams and kilojoules. So you're going to have to convert the grams into moles. So you're going to have to go find the molar mass of glucose to get that moles, that 2.5 grams into moles. And then when you get those moles, 39.0 kilojoules up top and the moles on the bottom. And let's go take a look at the math because I don't have a lot of room there. Okay, so what do we got? We have our grams that were given. Here's our molar mass of glucose to calculate moles, and then we put that on the bottom. And remember that this is a combustion reaction. Combustion reactions have a negative enthalpy, so there's a negative value there. So I think those are the trickiest spots, is to remember you need a negative in that spot. Part C. Okay, when oxygen is not available, glucose can be oxidized by fermentation. So here's our reaction this time, and we have a different delta H. It says there's a Kp given. So this Kp means it's very much left to right. Calculate the value of delta G. So first of all, I think delta G is going to have to be negative. Okay. Let's also talk about units. Delta G is going to be in kilojoules per mole. Okay. And then if you have a K and you want to find delta G, there's a little equation to do that with. This is in your equation sheet, so you don't have to memorize it. The negative RT, natural log K. Remember that the R in this case is not gas laws R, but energy. Now, when you get this, that R value is in joules, and that's going to give you a gigantic number of joules, and you can leave it like that, but typically people divide it by 1,000 to get it into a kilojoules number. Okay. So now that we have a delta G, and we have a delta H, and we have a temperature, we can solve for S. Now, very tricky. You have to remember that, well, in this case, not remember, because it's asked of you joules, and the delta G is in kilojoules, and the delta H is in kilojoules. So you're going to have to reconcile that and get those into the same units. So maybe what you could do is solve for delta S in kilojoules and then multiply it by 1,000 to get it into joules. And here's the work for that. So here is our delta H. Here is our delta G that we just calculated. Here's our temperature. And then so when you get that answer, it's going to have a kilojoules, but if you multiply it by 1,000, you get it into a joules. And if you would have done this math wrong, something would have went wrong there, you would have used this wrong answer to get a new answer for delta S. So you would have had the correct setup. You would have had the correct answer with your faulty answer from above. So you would have not gotten the point there, but you can get the points below. Okay, where are we at here? Part 3. Indicate whether the equilibrium constant for the fermentation reaction increases, decreases, remains the same if the temperature is increased. So let's go up here and let's look at what we got. The delta H is negative. That means that energy goes over here. So if you raise the temperature, it's as if you raised that energy and the reaction is going to shift that away. So will the equilibrium constant increase, decrease, stay the same? I think it's going to decrease because the shifting from right to left would give you a smaller number. Let's see what those guys, what the AP folks said. Okay, so they used the Le Chatelier's principle. Delta H negative, basically the same ideas that I had there. Oops. And our last part, part D, using the answer from part B and the information provided in part C, calculate delta H for this reaction. So this reaction is not, let's go, this reaction that's here is not the same as the reaction of part C. It's not the same reaction at the top of the question. So I think this is going to be a Hess's law kind of question. We have a delta H for that first reaction that we calculated in part B. We were given a delta H in part C. So we're going to use those two delta H's to get part D. Instead of me doing it with that little bit of room there, here's our two reactions. And looks like no rearrangement had to occur. So you just have to add those up. So it's going to give you a negative 1,370 kilojoules per mole. Oh, wait a minute. We did have to flip this one. Yeah, this reaction was given to you in that way. So yeah, so it was a negative 68 kilojoules and we flipped it. So sorry about that. So we did have a modification on that reaction. Okay. Still the same right answer.